I myself, Professor Bontu Shah, I am coming from the University of Burdwan, West Bengal. I will talk on the paper, namely functional analysis. The paper is divided into 10 chapters, chapter 1, 2, chapter 10, and each chapter consists of some modules. Today, I will start on chapter 1. It consists of 3 modules. Basically, the chapter starts with metric spaces. Actually, metric spaces plays a vital role in functional analysis. All the classical analysis, namely in real analysis, are in the particular cases of study in metric spaces. So, metric spaces are the generalizations of real analysis which are taught in undergraduate classes. This chapter is divided into 3 modules. Module 1 is concerned with some fundamentals, inequalities which are very essential in functional analysis. Module 2 is basically devoted on the study of metric spaces and some properties of completeness of a metric space. So, one important theorem, namely the Bayes category theorem, has been presented in module 3 of this chapter 1, is devoted on separability of metric spaces. The study of separability in metric spaces is very simpler than other non-separable spaces. In this module, we shall also deal with some properties on separable metric spaces and its subspaces. Now, I will talk on module 1 of this chapter 1, which consists of some fundamentals, inequalities which are very essential for functional analysis. I will talk on chapter 1. The title of the chapter 1 is metric spaces. Now, chapter 1 is started with module 1. This consists of fundamental inequalities. Now, we start with some basic definitions. Suppose we consider a set consisting of all sequences of real or complex numbers x is equal to xi I such that sigma I equal to 1 to infinity mod of xi I to the power p is less than plus infinity, where p is greater or equals to 1. The set is denoted by small l p and called the space of all bounded sequences of reals or complex scalars. Next definition, the class capital L P closed interval 0, 1 is the collection of all real valued measurable functions x t defined on closed interval 0, 1 such that integration 0 to 1 mod x t whole to the power p dt is strictly less than plus infinity, where p is greater or equals to 1. The first theorem is the following: if small a and b are real or complex numbers and p greater or equals to 1, then mod of a plus b whole to the power p is less or equals to 2 to the power p mod of a to the power p plus mod of b to the power p. Proof: case 1, if mod a is greater than mod b, then mod of a plus b is less or equals to mod a plus mod b is strictly less than 2 of mod a, and so mod of a plus b whole to the power p is less than 2 to the power p into mod of a to the power p less or equal to 2 to the power p mod of a to the power p plus mod of b to the power p. Case 2, if mod of b is greater or equals to mod a, then mod of a plus b is less or equals to mod a plus mod b less than 2 into mod b. So, mod of a plus b whole to the power p is strictly less than 2 to the power p mod of b to the power p. Hence, mod of a plus b whole to the power p is less or equals to 2 to the power p into mod of a to the power p plus mod of b to the power p. Thus, in either case, mod of a plus b whole to the power p is less or equals to 2 to the power p into mod of a to the power p plus mod of b to the power p. Now, we get a theorem if xt belongs to capital LP 01 and yt belongs to capital LP 01, where 0 is less or equals to t less or equals to 1, then xt plus yt belongs to LP 01 comma p greater or equals to 1. Proof: we have modulus of xt plus yt whole to the power p is less or equals to the power p modulus of xt whole to the power p plus modulus of yt whole to the power p. So, integration 0 to 1 modulus of xt plus yt whole to the power p dt is less or equals to 2 to the power p integration 0 to 1 mod of xt whole to the power p dt plus 0 to 1 modulus of yt whole to the power p dt. Since xt and yt both belongs to capital LP 01, the two integrals on the right hand side exist, and so integration 0 to 1 modulus of xt plus yt whole to the power p dt exists, which implies that xt plus yt belongs to LP 01. Similarly, we can show that xt minus yt belongs to LP 01. We get another theorem if x is equal to sequence ji belongs to small LP and y belongs to sequence eta belongs to LP, where p is greater or equals to 1, then x plus y is equal to sequence ji plus eta belongs to LP. The proof is that we have for each I modulus of ji plus eta to the power p is less or equals to 2 to the power p into modulus of ji to the power p plus modulus of eta to the power p, and hence sigma I equal to 1 to infinity mod of ji plus eta to the power p is less or equals to 2 to the power p into sigma I equal to infinity mod of ji to the power p plus sigma I equal to 1 to infinity mod of eta to the power p. Since x comma y belongs to small LP, sigma I equal to 1 to infinity mod of ji to the power p is strictly less than plus infinity, and sigma I equal to infinity mod of eta to the power p less than plus infinity, and so sigma I equal to 1 to infinity modulus of ji plus eta to the power p less than infinity, which implies that x plus y belongs to small LP. Similarly, it can be shown that x minus y belongs to small LP. The theorem: if a is greater or equals to 0, b is greater or equals to 0 and p greater than 1, then a into b is less or equals to a to the power p by p plus b to the power q by q, where 1 by p plus 1 by q is equal to 1. The proof: we first prove the following inequality: c to the power 1 by p into d to the power 1 by q is less or equals to c by p plus d by q, where c is greater or equals to 0 and d is greater or equals to 0. The inequality 2 is clear if c equal to 0 or d equal to 0, so we let c greater than 0 and d greater than 0. Proof: if 0 is less or equals to m is less or equals to 1, the function fx is equal to m into x minus 1 minus x to the power m minus 1 is non-decreasing for x greater or equals to 1, and hence fx is greater or equals to f1. Consequently, x to the power m minus 1 is less or equals to m into x minus 1 for x greater or equals to 1. If c is less or equals to d, then 3 is obtained from 4 by putting x is equal to d by c and m is equal to 1 by q. If c is greater than d, then 3 is obtained from 4 on putting x is equal to c by t and m is equal to 1 by p. In equation number 2, take c to the power 1 by p is equal to a and d to the power 1 by q is equal to b, and we get a into b is less or equals to a to the power p by p plus b to the power q by q, which is the equation number 2. The theorem is a very important theorem and is named as Holder's inequality for sums. If x is equal to sequence ji belongs to LP and y is equal to eta I belongs to LQ, where 1 by p plus 1 by q is equal to 1 as p is greater than 1, then sigma equal to 1 to infinity mod xi I eta is less or equals to sigma equal to 1 to infinity mod of xi I to the power p whole to the power 1 by p into sigma equal to 1 to infinity mod of eta I to the power q whole to the power 1 by q. Proof: take a is equal to mod of xi I divided by sigma equal to 1 to infinity mod of xi I to the power p whole to the power 1 by p, and b is equal to mod of eta I divided by sigma equal to 1 to infinity mod of eta I to the power q whole to the power 1 by q. Then by 2 we get mod of xi I into mod of eta I divided by sigma I equal to 1 to infinity mod of xi I to the power p whole to the power 1 by p into sigma I equal to 1 to infinity mod of eta I to the power q whole to the power 1 by q is less or equals to mod of xi I to the power p divided by p into sigma I equal to 1 to infinity mod of xi I to the power p plus mod of eta I to the power q divided by q into sigma I equal to 1 to infinity mod of eta I to the power q. So, sigma equal to infinity mod of xi I into mod of eta I divided by sigma equal to 1 to infinity mod of xi I to the power p whole to the power 1 by p into sigma equal to 1 to infinity mod of eta I to the power q whole to the power 1 by q is less or equals to 1 by p plus 1 by q is equal to 1 by assumption, and hence sigma equal to 1 to infinity mod of xi I eta I less or equals to sigma equal to 1 to infinity mod of xi I to the power p whole to the power 1 by p into sigma equal to 1 to infinity mod of eta I to the power q whole to the power 1 by q, and hence the inequality 5 follows. Now, the theorem is known as the Holder's inequality for integrals. If x t belongs to capital L p 0 1 and y t belongs to L q 0 1, where 1 by p plus 1 by q equal to 1 and p greater than 1, then integration 0 to 1 mod of x t into y t dt is less or equals to integration 0 to 1 mod of x t whole to the power p dt whole to the power 1 by p into 0 to 1 integration mod of y t whole to the power q dt whole to the power 1 by q, equation number 6. The proof is like this: put a is equal to mod of x t divided by integration 0 to 1 mod of x t whole to the power p dt whole to the power 1 by p, and b equal to mod of y t divided by integration 0 to 1 mod of y t whole to the power q dt whole to the power 1 by q. In equation number 2 we get mod of x t into mod of y t whole divided by integration 0 to 1 mod of x t whole to the power p dt whole to the power 1 by p. In 2 we get modulus of x t into mod of y t whole divided by integration 0 to 1 mod x t whole to the power p dt whole to the power 1 by p into integration 0 to 1 mod of y t whole to the power q dt whole to the power 1 by q is less or equals to modulus of x t whole to the power p divided by p into integration 0 to 1 mod x t whole to the power p dt whole to the power 1 by p plus mod of y t whole to the power q divided by q into integration 0 to 1 mod of y t whole to the power q dt whole to the power 1 by q. The proof: the right hand side of the above inequality involves integral functions and show the left hand side is also integrable. So, we get integration 0 to 1 mod x t into mod of y t dt divided by integration 0 to 1 mod x t whole to the power p dt whole to the power 1 by p into integration 0 to 1 mod y t whole to the power q dt whole to the power 1 by q is less or equals to 1 by p plus 1 by q is equal to 1, and hence integration 0 to 1 mod x t into y t dt is less or equals to integration 0 to 1 mod x t whole to the power p dt whole to the power 1 by p into integration 0 to 1 mod of y t whole to the power q dt whole to the power 1 by q, and consequently 6 follows. Theorem: Minkowski inequality for sums. If x is equal to sequence xi I belongs to L p and y equal to sequence eta I belongs to L p, where p is greater or equals to 1, then sigma I equal to 1 to infinity mod of xi I plus eta I whole to the power p whole to the power 1 by p is less or equals to sigma I equal to 1 to infinity mod of xi I to the power p whole to the power 1 by p plus sigma I equal to 1 to infinity mod of eta I to the power p whole to the power 1 by p. This equation is named as 7. The proof is like this: if z is equal to sequence xi I belongs to L p, then z dash is equal to sequence beta I whole to the power p minus 1 belongs to LQ, where 1 by p plus 1 by q is equal to 1, because mod beta I whole to the power p minus 1 whole to the power 1 by q is equal to mod of beta I whole to the power p minus 1 into q is equal to mod beta I whole to the power p minus 1 into p divided by p minus 1, that is equal to mod of beta I whole to the power p. And the convergence of the series I equal to 1 to infinity mod of beta I to the power p implies that of sigma I equal to 1 to infinity mod of beta I whole to the power p minus 1 whole to the power q. Now, sigma I equal to 1 to infinity mod of xi I plus eta I whole to the power p is equal to sigma I equal to 1 to infinity mod xi I plus eta I whole to the power p minus 1 into mod xi I plus eta I, which is less or equals to sigma I equal to 1 to infinity mod of xi I plus eta I whole to the power p minus 1 into mod of xi I plus sigma I equal to 1 to infinity mod of xi I plus eta I whole to the power p minus 1 into mod of eta I. This follows due to mod of xi I plus eta I whole to the power p minus 1. This sequence belongs to LQ and mod of xi I belongs to LP and mod of eta I belongs to LP. The proof is given below. Now, by applying the equation number 6 to each of the expressions on the right, we get sigma I equal to 1 to infinity mod of xi I plus eta I whole to the power p is less or equals to sigma I equal to 1 to infinity mod of xi I plus eta I whole to the power p minus 1 into q whole to the power 1 by q into sigma I equal to 1 to infinity mod of xi I to the power p whole to the power 1 by p plus sigma I equal to 1 to infinity mod of eta I to the power p whole to the power 1 by p. This is equal to sigma I equal to 1 to infinity mod of xi I plus eta I whole to the power p whole to the power 1 by q into, within the third bracket, sigma I equal to 1 to infinity mod of xi I to the power p whole to the power 1 by p plus sigma I equal to 1 to infinity mod of eta I whole to the power p whole to the power 1 by p. The proof is given below. Dividing both sides by sigma I equal to 1 to infinity mod of xi I plus eta I whole to the power p whole to the power 1 by q, and noting the fact 1 by p plus 1 by q is equal to 1, we get sigma I equal to 1 to infinity mod of xi I plus eta I whole to the power p whole to the power 1 by p is less or equals to sigma I equal to 1 to infinity mod of xi I to the power p whole to the power 1 by p plus sigma I equal to 1 to infinity mod of eta I to the power p whole to the power 1 by p, and therefore, the inequality 7 follows. Now, there is another important inequality known as Minkowski inequality for integrals. If function x t and y t belongs to capital L p 0 1 where p greater than 1, then integration 0 to 1 mod of x t plus y t whole to the power p dt is less or equals to integration 0 to 1 mod x t whole to the power p dt whole to the power 1 by p plus integration 0 to 1 mod of y t whole to the power p dt whole to the power 1 by p. This inequalities number is 8. The proof is given below. If z t belongs to capital L p 01, then modulus of z t to the power p minus 1 belongs to capital L q 01, where 1 by p plus 1 by q is equal to 1. Because of the fact mod z t to the power p minus 1 whole to the power q is equal to mod of z t whole to the power p minus 1 into p divided by p minus 1 is equal to mod of z t whole to the power p, and since z t belongs to capital L p 01, it follows that modulus of z t to the power p minus 1 whole to the power q is integrable, that is mod of z t whole to the power p minus 1 belongs to capital L q 01. The proof: integration 0 to 1 mod of x t plus y t whole to the power p dt is equal to 0 to 1 mod of x t plus y t whole to the power p minus 1 into mod of x t plus y t dt is less or equals to integration 0 to 1 mod of x t plus y t whole to the power p minus 1 into mod x t dt plus integration 0 to 1 mod x t plus y t whole to the power p minus 1 into mod y t dt. Now, by the above fact and by above theorem, modulus of x t plus y t whole to the power p minus 1 belongs to L q 01. Also, we have x t comma y t belongs to capital L p 01. The proof is like this: by applying Holder inequality that appears in sets for integrals to each of the integrals on the right side, we get integration 0 to 1 mod x t plus y t whole to the power p dt is less or equals to integration 0 to 1 mod x t plus y t whole to the power p minus 1 into q dt whole to the power 1 by q into integration 0 to 1 mod x t whole to the power p dt whole to the power 1 by p plus integration 0 to 1 mod x t by t whole to the power p minus 1 into q dt whole to the power 1 by q into integration 0 to 1 mod y t whole to the power p dt whole to the power 1 by p, which is equal to integration 0 to 1 mod x t plus y t whole to the power p dt whole to the power 1 by q into, within the third bracket, integration 0 to 1 mod x t whole to the power p dt whole to the power 1 by p plus integration 0 to 1 mod y t whole to the power p dt whole to the power 1 by p, third bracket closed. Dividing both sides by integration 0 to 1 mod x t plus y t whole to the power p dt to the power 1 by q, and by using 1 by p plus 1 by q is equal to 1, we get integration 0 to 1 mod x t plus y t whole to the power p dt whole to the power 1 by p is less or equals to integration 0 to 1 mod x t whole to the power p dt whole to the power 1 by p plus integration 0 to 1 mod of y t whole to the power p dt whole to the power 1 by p. Just now we have finished with an important inequality, namely Minkowski inequality for integrals. Now we can set another type of integral, and it can be left for an exercise to the readers. If 0 less than p less than 1 and q be such that 1 by p plus 1 by q is equal to 1, and if f belongs to capital L P A B and g belongs to capital L Q A B, then integration a to b mod f g dt is greater or equals to integration 0 to 1 mod of f t whole to the power p dt whole to the power 1 by p into mod of g t whole to the power q dt whole to the power 1 by q. So, the module 1 is finished with fundamental inequalities, which are very essential in function analysis, and that will be helpful and will be applied for another chapters that will be discussed later on. With these ideas as discussed in module 1 of this chapter 1, we now close module 1 of this chapter 1.